So as I alluded to, I have one story, but it's potentially the biggest story in astronomy, and many of you have probably already heard about this, which is the imaging of the black hole in the galaxy M87. And so this is a graphic that was made by, I think, the European Southern Observatory. But this is a really big story, not only because it's so monumental in just the job that the astronomers had, but also because of the team. There are more than 200, or about roughly 200 astronomers involved, dozens of different institutions, on the order of about a dozen different funding agencies. And so this is really, really big science. And it also, and so this is the image that you probably saw in the news. And what we're seeing is the first picture of a black hole, and this is in radio. So this is not an image reconstructed with the wavelengths of light that we can see with our eyes, the visible wavelengths, but this is in the radio regime. And this, as we will see, this image of the black hole is actually what astronomers and physicists have been predicting for many decades. And so this is sort of a fruition of many decades worth of work by probably hundreds, if not many thousands of people, not only working on this project, but working on all the science that has led to the possibility of doing this amazing, or creating this amazing picture. And so this appeared on the front page of the New York Times, but because this was an international collaboration with astronomers on virtually every continent, even in Antarctica, were participating, even though nobody actually lives in Antarctica full time. So there are pictures, here are pictures from the Spanish language press from around the world. This was posted on Twitter by astronomers at the Smithsonian Astrophysical Observatory, where they're shown holding pictures of different newspapers from around the country that all had the picture on their front page above the fold. And so the question is, how was this done, and what exactly is the science behind this? So this is a big story, and that sort of explains why I'm just going to focus on this one particular story before I hand it off to Steve. So to really start explaining this, we actually have to go back more than 100 years, and we have to talk about Albert Einstein. Albert Einstein came up with his theories of relativity just over 100 years ago, and had the first one called the special relativity in 1905, and then 8 years later, in 1913, he had the general theory of relativity. And what Einstein did was to force us to really rethink about how we think about our universe. And so before Einstein, we often think of space and time as these very separate things. I mean, they're somewhat abstract terms, but we think of space as sort of like the stage, this big volume of space. And then time is a little bit harder to explain, but I think one comedian explained it as the universe's way of preventing everything from happening all at once. So that's time. But what Einstein realized, and he has been proven basically correct in all of his ideas about relativity since then, is that space and time are actually two aspects of the same thing, and you can't talk about one without including the other. And so Einstein introduced this concept of space-time. So instead of just a three-dimensional space where we think of a volume of space that has a length, a width, and a height, you have to include a component of time as well. So there's actually 4 dimensions of space-time. Next, Einstein also came up with this idea that energy and matter are also related by this equation, which is perhaps one of the most famous equations in all of science. Energy is equal to mass times the speed of light squared. And this, again, is an idea that has been proven to be correct since Einstein introduced this idea. But this basically says that you can convert energy into matter and matter back into energy. And because the speed of light is so big, even for a small amount of matter, that means you can actually get a huge amount of energy coming out of it. Now, those two principles were introduced in the special theory of relativity, but what he did in the general theory was to sort of combine the two. And what he showed was that space-time and matter and energy interact with each other. They actually affect each other. And the way they affect each other is that matter and energy can distort space-time, and with space-time distorted, that space-time can affect how matter and energy traverse through the volume of space-time. And so that's kind of a complicated thing to imagine, but the way to think about it is that instead of trying to explain gravity as a force that pulls on things, what gravity is actually, how gravity actually works is it's due to space-time itself being distorted by the presence of matter and energy within space-time. And once you have that distortion of space-time, the effects of gravity is basically due to that curvature of space-time altering the trajectories of things that travel through space and time. And so the orbit of the Earth around the sun is due to the distortion of space-time by the mass of the sun, and the Earth naturally traces a path around the sun because of that distortion. And a lot of the ways that people visualize space-time being distorted is to think of it like your mattress when you lay down on it, or you put a bowling ball, and your mattress or the fabric of space-time gets distorted. So this is a visual of how you can imagine it, but you can't really fully describe it without some complicated mathematics. But one of the ideas that led to black holes is the thought of what would happen if you had a very dense mass, and at some point you could actually create an almost infinite curvature in the space-time. And so if you had an ordinary mass like the sun, you would create a dimple, and if you had something more massive, you create a larger dimple in space-time. But a black hole would be something that you could think of as almost puncturing space-time or pulling it down infinitely far. Another way to think about it, so since Einstein's time, physicists and astronomers have spent a lot of time thinking about what black holes must be like and trying to make observations of things that we think are black holes. And basically we have a very rough picture of what black holes might look like. One is we have what's known as the event horizon, and this is the part of the black hole that's still somewhat far away from the center, but this is the part where light cannot escape. So the escape velocity is so high that anything that falls past this perimeter, the event horizon, will never come back. And so, so that's effectively why black holes appear black, because the escape velocity is greater than the speed of light. And the reason why we can observe black holes today is because most black holes, or many black holes, have accretion disks. Material falling towards a black hole piles up into a disk, and instead of falling straight in, they slowly spiral in. But because this gas and other matter is rubbing against other gas, you have a lot of friction that heats up this accretion disk, and so there's a lot of radiation that can be generated, a lot of heat, and so we were seeing energy from the accretion disk. And there's even ideas, especially for supermassive black holes, that there are magnetic fields that thread through the event horizon, and that can help generate jets of material. And so another way that we can see black holes is through these super fast jets that send out material far out into space. Here's another visualization of what is happening in a black hole. So this is the event horizon. And one idea to think about what is occurring in a black hole is that space-time itself is actually flowing in or falling into the black hole. And so as it's getting closer and closer, space-time is actually speeding up faster and faster. And the event horizon is basically the point at which space-time is flowing at the speed of light into the black hole. So that means that even if you're traveling at the speed of light, once you hit that event horizon, you will inexorably get sucked in towards the singularity, the center of the black hole. So astronomers have been looking for black holes for a long time, and all of the evidence that we have for them up until recently has been indirect, meaning we have evidence of black holes circling other stars. black holes that were born out of binary systems where one of the stars went supernova and part of the core collapsed into a black hole. And so the remnant binary pair, the black hole is now accreting material from the outer envelope of its partner star. And so the reason why we see that black hole is not because we can actually observe the event horizon, but because we can observe the radiation coming from the accretion disk. These objects are so far away, and the detail that we're trying to observe would be so small that we wouldn't be able to see it with an ordinary telescope. So the only thing that we can see is the radiation coming from the accretion disk. And similarly, when we look out at other galaxies, and even in our galaxy, we find that virtually all other galaxies, or most galaxies, have evidence of not only a black hole at the centers, but supermassive black holes. Our galaxy, the Milky Way, has a black hole about 4 million times the mass of our sun. And there are galaxies that have much more massive black holes. And the most massive black holes seem to also have much more gas coming in, and so they tend to also have much more activity, like jets and sporadic outbursts of radiation. And that leads us to M87, which is a galaxy about 55 million light years away. It's in the constellation Virgo. It's part of the Virgo supercluster, which is a giant cluster of at least 2,000 galaxies. And our Milky Way and our local group of galaxies are all falling towards the Virgo supercluster. And M87 is an elliptical galaxy, so unlike our Milky Way, which is a spiral with a flattened disk and spiral arms, the elliptical galaxy just has kind of a blobby elliptical shape. But here you can see that even you can see the hint of the jet that's erupting out of M87. So we've known for a really long time of this indirect evidence for a giant black hole in the center of M87. And in this picture, you can see the other galaxies that are part of Virgo. There are a lot more, but those are some of the closer ones. And so here's yet another, this is an artist's depiction of what the center of M87 might look like with a large, massive accretion disk, and then the jets coming out. So that brings us to the Event Horizon Telescope, which is the collaboration that led to the black hole picture. And so there, some of the goals are basically to create the first direct image, so not indirect evidence for a black hole, but to actually image the black hole directly. And the reason why they want to do this is to test general relativity. So general relativity has passed with flying colors in all the observational tests that we've been able to make of it. But for the most part, most of those tests involve somewhat low mass situations. So not extreme gravitational scenarios like you'd find in black holes. So as a further test, we want to see if our predictions from general relativity match our observations when you're looking at a black hole up close. And then once you're able to image the black hole, then you can actually observe matter that's being drawn in, and that can help improve your models of how the radiation and the jets are being emitted from the black holes themselves, or from the accretion disks around the black holes. So in order to sort of explain how telescopes work and how the Event Horizon Telescope works, I have to introduce this equation. And this is an equation that describes the detail that a telescope can observe. And so there's some terms that are in Greek. This is the Greek letter theta, and this is the Greek letter lambda. And these are somewhat standard. But what it basically means is that the resolution, or the amount of detail, how small of a bit of detail that you can see with your telescope, depends on basically two factors. One is the wavelength of light that you're observing, and so, and then the other is the diameter of the telescope. And if you think about this algebraically, what this means is that the smaller the wavelength of light, the finer detail that you can see. And what this also means is that when you're dividing by the diameter of the telescope, the larger the diameter, the smaller this number becomes overall. And so that tells you if you go to larger and larger telescopes, you can, again, see finer and finer detail. And this basically has to do with how telescopes can resolve, let's say, point sources. And so if you have a telescope that's not quite large enough, it might see a pair of point sources as one because they're just blurred together. But as you improve the resolution of the telescope, either by going to shorter wavelengths or by going to larger telescope diameters, you can basically resolve or tell that there are 2 point sources instead of just 1 point source. And the reason why we want to do this is that why we want to go to higher and higher resolution, or to be able to see smaller and finer detail, is that there's lots of stuff out there in the universe that are either so small or so far away that they're very difficult to observe. And so this plot basically shows along this axis the size of something. So 1 degree is about twice the size of a full moon. And then if you divide that degree into 60, what we call arc minutes, and then divide each arc minute into 60 arc seconds, here's 1 arc second, and here's 0.1, 0.01. This M stands for milli arc second, so that's 1,000th of an arc second. And then you can continue on. And so what the new Event Horizon Telescope is trying to do, it's trying to get down to the micro arc second level. So somewhere around here. And when we look at telescopes that here's the human eye. So our resolution is just around 1 arc minute. So that's how much detail that you can see. So someone with 20/20 vision, when you're looking at an eye chart at the eye doctors, the smallest element of those letters is about 1 arc minute. And then here's the Hubble Space Telescope. Here's one of the largest ground-based telescopes. And it turns out there's a technique called interferometry where you can combine multiple telescopes. And when you do that, you can actually get down to much lower or higher resolution, greater detail. And what happens when you combine telescopes, and this is most easily done in the radio, is instead of that D being the diameter of the telescope, now what you're dividing by is the baseline, which is the separation between the telescopes. So if the telescopes, or if you have pairs of telescopes that are separated by hundreds of meters, or even by kilometers, you can imagine this B can become very big. And so when you divide this by a very big number, this becomes very small. And that means you can see much finer resolution. The caveat with radio is that the wavelength of radio is actually much larger than, let's say, at visible wavelengths. So instead of, when we talk about the wavelengths that we see, we're talking about hundreds of nanometers, which are tens of billions of meters. But here in the radio, you can often talk about centimeter to meter size wavelengths. And so in order to compensate for the fact that your wavelengths are much longer, you have to go with really big baselines. So for the Event Horizon Telescope, they basically converted or outfitted a number of different telescopes around the world. So there's one at the South Pole Telescope. There's a whole interferometric array, ALMA, in Chile. And then there's one in Mexico, the sub-millimeter telescope in Arizona, outside of Tucson. There's one in Spain, and then a couple of dishes in Hawaii as well. And so the idea is that instead of having a telescope that's the size of the Earth, you're reconstructing a telescope whose baselines effectively span the globe. And so when you think about how big these baselines are, and going back to that equation, you can imagine you can have really fine detail that you can see. And now, when you are creating images using interferometers or interferometric telescopes, you don't actually create images like you would do when you're taking a picture with your camera or with a normal telescope. And that's because when you go back and look at this, you have to mathematically combine the signal from all these different telescopes in order to create the image. And so it becomes a mathematical exercise, and there's a process that I won't go into, but it's called Fourier transform that basically computes an image based on the spatial frequencies that are being observed. And what I mean by that is that, I keep going back to the slide, so let me just go back again. What this means is that when you have a really long baseline, you can see very fine detail between, let's say, this telescope and that telescope. And when you compare this telescope with that telescope, since their baseline is shorter, the amount of detail that you can see isn't as fine, so it's coarser. But what it also means is that this pair of telescopes won't give you any fine detail. It will only give you coarse detail corresponding to this particular baseline, whereas this baseline here will give you super fine detail corresponding to this baseline, but it won't give you any coarse detail at all. So what this means is that different pairs of telescopes will give you different types of detail. And you need to combine baselines from all the different instruments in order to get detail at different levels of spatial resolution. And the way to think about that is if we converted this data into a sort of a mathematical function of what the detail would look like from, let's say, a set of telescopes, you might get a pattern like this. And then you'd have to mathematically transform this back into your image. So the data that the telescopes return can't be processed until you run it through computer algorithms and software in order to pull out the spatial detail. And so in this case, I've taken a picture and deconstructed it into the basic spatial detail. So there's low resolution detail in the center, and then there's high resolution detail off at the edges. Can you guess what this picture is of? You can't, because our minds don't operate algorithmically. But here is what it is. So it's the museum. But if you go through this convolution exercise, you get that weird mathematical 2D image. Here's another picture that's slightly different, but again, there's nothing you can say about what this image is of. But if you work backwards through that convolution, you get a picture of this. So basically, this is what the astronomers are trying to do. But instead of having a nice filled image where you have detail at all scales, at small scales as well as large scales out here, what astronomers have is they only have so many different stations and so many different baselines. And so this is the coverage. And so each of these stripes represent a different pair of baselines from the different telescopes. And then when you, as the Earth rotates, you also get additional coverage. So the baseline is changing as the Earth rotates. So what they did was they observed back in 2017 over a period of 4 days. And in the particular wavelength that they observed at 1.3 millimeters, that's actually really sensitive to the amount of water vapor in the atmosphere, which is why many of these telescopes are at very high and dry sites. But that means if you're clouded over at one site, that ruins the observing at all the other sites as well. So you need to have perfect weather at all of your locations. And they have baselines anywhere from 160 meters to 10,000 kilometers. And the theoretical resolution is down to 25 microarcseconds. And so what they do is they do all of their observations, and then they actually have to carry or fly the data to a central computing centers where they do what they call a correlation to combine the data, and then they reconstruct the image. And so here's a picture of someone at the South Pole packing up about 1,000, the total amount of data is about 1,000 pounds worth of hard drives. So this is just a fraction of that. So maybe this might only be 100 or a couple hundred pounds of hard drives. And then after a couple weeks, it ends up in one of two data centers. This is the one at the MIT Haystack Observatory in Western Massachusetts. So you can see them opening up the boxes, and then here it is. This is 5 petabytes of data from all of the telescopes. And there is so much data here that the internet is just not fast enough to transmit all this data, which is why shipping it is far faster, probably on the order of maybe 100 times faster. But one astronomer estimated that this amount of data would be equivalent to about 5,000 years of MP3 music. So here is the hard drives stored in their little library. And then they go through the process of creating the images, or the image. And this is the full image that you saw earlier. But here's an image where they left out 2 of the observatories, or the ones in Chile. So you can tell how by excluding one set of baselines, that can completely negate the picture that you can get, just because you're losing crucial information about specific spatial information that's in that final image. And here is a look at each day's worth of data. So April 5th, 6th, 10th, and 11th. And the image that you saw in the press was a combination of these 4 days with the data. And then these additional rows are where they left out part of the data for their processing. And there might be variations in the brightness of that ring that we're seeing here, although that's not quite completely certain. Here is where they're comparing their models of what happens when light is being emitted very close to the black hole. And so light can orbit the black hole in strange ways before it comes to us. And so these are the different models of what the black hole would look like if you were right up close to it, observing at that particular wavelength. And then after they process it through their simulated Event Horizon Telescope observations, this is what each of these models looks like. So you can see that the theoretical models can actually look very much like what we observe. And then finally, we can, by observing or measuring the diameter of that hole, we can estimate how big the black hole is. And so this is one of the best estimates of the size of a black hole that we have. For M87, it's about 6.5 billion solar masses. And it's actually larger than earlier estimates using other indirect techniques. And then here yet is another model. So this is the observed M87 black hole. This is their particular model. And in this particular model, they actually also model the jet that's coming out. And they, again, show that their model is very consistent with the observation. And then the cartoon XACD posted how big this black hole is compared to our solar system. So you can see that Pluto's orbit is well inside the event horizon of that black hole. And so these supermassive black holes are basically the sizes of solar systems. That gives you a sense of how big they are. And so with that, I want to hand it over to Steve. And I'll be able to answer questions at the end.